Okay, so we're recording. Um, Thank you for joining us, and let's do some house cleaning item. Test is Thursday. Alex, no, we're gonna move the test next week. There are two reasons. One, I have checked with our faculty members in the department. Based on their feedback, we decided to do a take-home, so there will be no proctoring. And also, what we'll do is we're going to have a time frame for you guys to work on it. So basically, we'll send out a problem in so and so time, and we'll let you guys work on it, and then return it with so and so time. So it is crucial to have a common time, which everybody is available to work on it. So we have decided to move it to next week, next Thursday. And on next Thursday, we will have the exam paper upload on a specific time on the Canvas. So you can retrieve that and start working on it. And then once you finish, we require you guys to take a photograph. Basically, just take a snapshot from your cell phone and then upload the solutions together with your exam sheet and the crib sheet to the Canvas. Okay. And since the Canvas have the time mark, so we will be able to determine whether you're turning on time or not automatically. Okay. And I haven't decided on how many problems exactly there are yet, but I worked on it a little bit in the weekends. So far, it will cover the shear and also the one-way slab, and these will be the main components. But still, we want to pick up a little bit T-beam and what we talk about from flexure a little bit, depending on the time. So these will be the focus. Yes, we'll go over all the exam like we did for the first exam, but that exam lectures will not be recorded. And yes, we'll probably set up a time next Monday to go over it, or this Thursday, depends on how fast we go with our course content. But let me say this again, they will not be recorded, okay? So we will have a review sort of slash going over all the exam session for it, okay? And now also for the homework, since we have a issue on this continuous slab design because we haven't finished the frame yet, which is a continuous one yet. So you find yourself in a little bit awkward situation because there's a problem in the homework that you cannot finish on last week. So we extend the deadline to next Monday, so you have time to finish. And after today's lecture, you should be able to finish them all, okay? All right, so that's all we have with all our exams. You're welcome for the second midterm and everything. And we're running a little bit short on time, not because delay or anything from the syllabus or from the virus. It's just because we would like to have more information sent to you guys this semester since we're doing a video online. So I'm a little bit experimenting as well. But that can be a good thing because we're not, most likely will not have the third midterm anymore. But I have to see the syllabus and also the schedule to see. But keep in mind, if we don't have the third midterm, well, we're just gonna have the final. We might have to do a lump sum of final, but focus more on the column design. So it's either gonna be segmental or altogether. So we have to discuss a little bit. Jacob, the data exam is set for next Thursday, okay? Not this week, next Thursday, okay? It's a little bit late, okay? And the content will cover the one-way slab, both simply supported and continuous, and the shear design, okay? And we'll have a review session next Monday, probably in the afternoon as well, to go over some of the content and maybe go over the old exam. If we're running fast, we probably can do it this Thursday, but we have to see, okay? So that's the update I have. That's what we have so far. If there are no questions, we're just gonna proceed, okay? Because time is precious, all right? So last time we talked about one-way slab, and turns out there's got to be some strategy we have to apply to get the maximum moment, right? So recall the influence line concept, right? Influence line concept. Oh, sorry, you don't have to worry about it, but just continued one-way slab. Okay. So the influence line concept, okay? It pretty much said if I have a continuous spans of slab or beam, as a matter of fact, it can be either way, and I want to solve for the maximum moment for a particular section. Let's just say I want to solve for a maximum moment in this section right here, okay? And to do that, I first draw the influence line. Okay, so I'm gonna use red. How do I draw influence line? I break this element, and this depends on whether it's a moment or force I'm requesting. Say in this case, it's maximum moment, okay? What I'll do is I will remove that and replace with the relative degree of freedom, which in this case is rotation. So I break it and open it like that, okay? And once I break it and open it like that, right? It will give me a line just like this, okay? Okay, just like that. So this is the influence line. That means I have values, of course, on these lines. That means if I have a vertical load, blue here. All right, if I have a vertical load, okay, say I call it MB on the influence line. Okay, so that means the actual maximum moment at MB, or the moment at MB caused by this load P here is gonna be P multiplied by MB L at location P. Okay, so this is the MBIL at location P. This value here, okay? This value here, okay? So that's the concept of influence line. That means if I draw an influence line, that means I will have a value, okay? And then you can multiply that value with the applied load at that location to get a moment at the corresponding section you're looking for, right? So that's the concept. That's the concept of influence line here. All right. So naturally, if I have a distributed load, okay, if I have distributed load, and I want to have a maximum moment, say MB and positive. Excuse me, I'm not fully recovered yet, apparently. Anyway, so in this case, I will have a distributed load, right? And this is omega u, okay? Because you see all these values are positive. All right, again, sorry, I have a reverse sign that you guys do, okay? So this for me is a positive, okay? For me is a positive, okay? So I have all these are positive, right? So I'm gonna, if I want to find the maximum positive, I'm just gonna load it up, right? To have the positive, okay? So that's the pattern that we're looking for. That's the pattern we're looking for. Okay. So on and so forth, so on and so forth. So on and so forth, okay? To find out the positive moment and negative maximum moment. So this is normally what we do to find the maximum moment on the structure, okay? So let me write it up for you, okay? So this is what we do normally, okay? So say pattern loading, okay? So this is called pattern loading. Okay, so ACI 318 at section A, 0.11.2 defines that, okay, loading patterns. To determine the maximum design moment. Also share design moment, maximum design moment, and also share. Okay, for or in continuous one-way slabs, continuous beams, and one-way slab. Okay, all right. So this is how they design it. Actually, this is how they define it. They say first, you either have a factored dead load on all spans, okay, and factored live load on two adjacent spans. Okay, and that's it. Okay, and the other pattern, now we all know it, it's got to be factored dead load on all spans. All right, on all spans, and plus factored live load on alternative or alternate spans. Okay, alternate spans. What does it mean? It means this figure right here. Okay, it means this figure right here. So for ACI, all right, ACI it says, all right, so I'm going to label this out. The maximum positive moment, okay, maximum positive moment in the exterior spans, okay, in the exterior spans means right here, A, or this is A1, or the minimum positive moments in the center span, A2, and the maximum negative moments at interior faces of the exterior column, A3. Okay, so let's show them clearly. This is the structure, right? I have a column, I have beam or slab. All right, these are called exterior. And this is exterior span as well. This is exterior span. And this is interior. Okay, and now the first case, right? A, it says maximum positive moments in the exterior span means maximum positive moment. So normally this is talking about the maximum positive moment here. Somewhere, sorry. Maximum positive moment here. Okay, so this is A1. That means if you want to achieve the maximum positive moment at exterior spans, here and here, you apply this loading pattern. Okay, what is this loading pattern? Now, the dead load is right here, all spans, okay? And the live loads are on exterior spans. The live loads on exterior spans. Okay, second, the minimum positive moment in the center span. The minimum positive moment. So this is MIN, minimum positive. Okay, and this is also from this diagram here. And A3, the maximum negative moment in the interior face of the exterior columns. What does that mean, right? What does that mean, right? So this is a little bit complicated. So first of all, the exterior column is right here. Okay, this is the exterior columns. And if I want to draw it in the 3D view, right? So it's gonna be something like this. Okay, something like this. Isn't it? Horrible drawing, but that's more like it, right? That's the column, right? But if I really want to show it, right? I want to zoom in to show it, right? So I have a column here. This is my beam or slab. This is my column. okay, says exterior column, interior faces. Interior faces means the moment here, okay? Moment here, cut, right? So cut 1, cut 2, okay? So this is 1, and this is 2. Okay. Okay, so that's is called interior face, which is actually this side. Okay, that's just what they call it. And that's why, because 1 and 2 has to match almost, okay? Basically, in this symmetric conditions, 1, 2, 3, 4, total moment has to balance each other. Total moment has to balance each other. Now, when we say interior, it means this side, okay? This side. So 1, 2, 2, 3, okay? Not 1, 4, nor 3, 4. Right? So this is called the exterior column interior surface. Interior surface. Right? What is saying? What does it mean? Means if you want to find these items, if you want to find the maximum moment in the exterior span, the minimum possible moment in the interior span, and if you want to find the maximum negative moment in the interior surface of the exterior column, use diagram A. Use diagram A. All right. And then if you want to find a maximum positive moment in the center span, minimum positive moment in the exterior span, and then all these nice terms, right? All these nice terms, right? Then you use B or C. Okay. I'm not going to go in detail. Once you understand how this is dictated, you can read through. Okay, you can read through, understand. Okay, you can read through, understand. And the loading the moment diagram. Okay, the envelope. What does envelope mean? Means the maximum moment line. Okay, the maximum moment line. The envelope for moments look like this, and the maximum the diagram for shear look like this. Look like this. Okay, so this is rather complicated. This is rather complicated. Why? Because it seems like ACI wants you to show these loading patterns. Pattern A, pattern B, pattern 3, and then generate an envelope for moment and shear. Then go in to find out the corresponding maximum moment, maximum positive, maximum negative, minimum positive, minimum negative, exterior, interior, interior surfaces of the exterior column. Is just yada, yada, yada. It's a long list. Long list, and it's very hard to do. It's very hard to do. Is that right? So to do this is a very long process. A very long process. Okay. Now this, although very long, it is the most accurate, the most efficient way to do it. Most efficient way to do it. And you probably guessed it. We are not going to do that in our exam. In our exam, in our course, we're going to probably do that, but not in our exam. Okay, not exam. So. So apparently ACI says, if you don't like this approach, which is a bit long, and you want to do it faster, and also if you have an ideal situation, which I'll explain what are the ideal situation, you can do a different approach. You apparently can do a different approach. What is this a different approach? This is called approximate analysis. Okay. What is approximate analysis? This is so-called actually, oh, sorry, something messed up with one pad. Okay, just a second, let me recover it. Okay. Something's not right. Okay. Okay, let me try to do it again. Okay, so this is called the ACI moment coefficient approach. ACI moment coefficients. Okay, all right, so the ACI says, if you don't like this approach, all right, ACI, moment coefficient, can be applied to determine the maximum moment shear. In continuous beams and one-way slabs. Okay, and be careful, right? This is subjected to vertical loading. All right, but this does not count without a price. Okay, this has applied limitations. Means only if you satisfy the following conditions, you can use this moment coefficients. And yet, to explain to you what are the moment coefficients. Okay, so just bear with me a second. Just bear with me a second. Okay, so what are those? What are those limitations? What are those limitations? Here we go. So first of all, it has to have 2 or more spans. Of course, right? If it's less than 2 spans, it's not a continuous span anymore. Okay. Second of all, span lengths approximately equal, almost the same span lengths. Okay, with longer. So what is approximately equal, right? With a longer of 2 adjacent spans. Sorry, let me just wipe this out. 2 adjacent spans, not 20% greater than the shorter one. Means the longer of the 2 adjacent spans cannot be over 20% longer than the shorter one. Okay, and then continue. 3, it has to be uniformly distributed load to use it. Okay, has to be uniformly distributed load to unit to use it. 4, the live load, all right, does not exceed 3 times of dead load. And keep in mind, and this is unfactored. Okay, before you factor, you need to check whether the live load exceeds 3 times the dead load. All right, and the last but not least, only apply to prismatic members. The oval and circular shape columns cannot be used. Okay, so it only applies to this in your head. You can think of this, only apply to this. It's either going to be this or this continuous monolithic cast. Okay. Okay, and don't forget, if normally we have 1.2 dead plus 1.6 live, and now if you have 1.4 dead load governs. Okay, if that governs, moment coefficient should not be used. Okay, okay, so this is very important. All right, okay, so we have talked about the limitations, and then let's take a look at it. What is the moment coefficient you're so promoting about, right? This is it. This is it. Okay, and you can see that you can find this from ACI 6.6-5-I-2. I wonder if this is the textbook. I think this is the textbook. Well, nevertheless, you can use this, okay? This is still valid. All right, so let's go over the little bit real quick, okay? So if I want to find out a positive moment, if I want to find out a positive moment at end spans, two ends, if it's discontinuous and is unrestrained, okay, we'll talk about this unrestrained. But normally unrestrained means if it's just like this, simply supported conditions. Okay, comparing to restrained, it's more like a U or L, right? L shape. Okay, so if discontinuous end is integral with support interior spans, right? So these are this. Okay, these are this. All right, but you can draw this on it, but I don't want to keep this because it'll muddy the water. So we'll just take a look at the table only. All right, so if I have a end span and the end is discontinuous, unrestrained, I use this number right here. Okay, I use this coefficient here. What is this coefficient? 1/11 omega u is the factor load ln squared, okay? And you see there's a small sign here, right? It reads here, omega u is the total factor load per unit length of the beam or per unit area of the slab. Means omega u equal to 1.2 omega dead load plus 1.6 omega live load. Okay, and second, Ln is the clear span of positive moment shear and average of the two adjacent clear spans for negative moment. Means if I have this, okay, all right, and then the span length usually is from the center to center. The Ln is actually from interior surface to interior surface. Okay, and be careful, say clear span for positive moment and shear, and the average of the two adjacent clear spans for negatives moment. So if you have, right, if you're trying to find a positive moment, maximum positive moment for this particular span, then you use Ln. You use Ln. If you want to find out, the negative moment at the end of the span, right? Then you have one span and left span and right. So Ln1, Ln2, then your Ln equal to half of Ln1 plus Ln2 average. Okay, and same thing here on this side as well. Okay, be careful, right? Be careful. Okay, so this is the difference. And also here, let's continue down the list. If it's interior spans, you use this. And negative moment exterior surface of the first interior support, use this. Okay, and so on and so forth. With all this limitations, all these limitations. All right, so this is the coefficient table you will need to use to calculate the maximum moment and shear. In our case, since we're designing one-way slab mainly for moment, so it's mainly for moment. All right, this is mainly for moment. Okay, all right, so here's an example, right? Here's an example. And that table is actually converted to this nice drawing here, All right, so in case 1A, I have beams with more than 2 spans. This is a beam with more than 2 spans, right? And then these are the coefficient, right? So if you see from my drawing here, the positive means it is the maximum positive moment at the middle span, and these are the coefficients. Now, you see 1/11, you see 1/14, and 1/14 again here, right? This is the list I'm talking about. And 1/11 corresponding to discontinuous and with unrestrained which means this is continuous and 1 here, simply supported, right? Unrestrained. I use 1 over 11, all right? And the end, negative moment, I then use 0, okay? Here, I use 111. If I have a spandrel, means 2, I have an L shape, right? Which means the slab cast in to the column. This you usually see from the parking lot, all right? This is top floor, basically, okay? I use 1 over 24 or 1 over 14, and these are the rest of the numbers. If I have a column, which is the third case, right? This is the column, it means in the middle floor, all right? And then I use 1 over 16 and 1 over 14, all right? Now, you see all these numbers here for case 3 and 1 are now showing means they have the same, right? They have the same. If they're different, they list them out, okay? All right, so following the similar case, right? This is basically for case 2 being with 2 spans only, right? Only 2 span, no more third span, okay? So there's no span. That's it, just 2 spans. Okay, case C, slab with spans not exceeding 10 feet. So this is a slab, okay? Now be careful, these are beams, all right? Okay, these are slab. Okay, so slab with span not exceeding 10 feet. So Ln smaller than 10 feet. Okay, so I use this table right here. All right, D, beams in which the sum of column stiffness exceed 8 times the sum of beam stiffness each end of the span. That means the bending stiffness of the column, top and bottom plus together, exceed 8 times the sum of the beam stiffness each end of the span. Oh, so if the total stiffness of the column, right, means like this, okay, is much stiffer than all the beam ends moment resistance, I use this. What does it mean? So comparing this table right here, 1 over 12, 1 over 14, 1 over 12, right? You notice that, especially the end here, 1 over 12, this data is bigger than previously 1 over 24. Oh, my pencil died again. So sorry. Give me a second. Okay. It's probably not the pencil problem. All right, here it's not a pencil problem. Okay, so if I have a stiffer, this means stiffer column and soft beams. Okay, stiffer column, soft beams. I have higher, higher moment coefficient than normal. In this case, right, higher means 1 over 12. Okay, it's bigger than 1 over 24, 1 over 16. Okay, just because in this case, right, in this case, I have a softer beam, so the moment will always go into the beams. The moment will all go into the beams. Okay, all right, so that's the table and that's the figure. All right, so this is the table you need, and this is the figure you need. Okay, my recommendation is you go over both of them and make a crib sheet out of them two both together. Okay, I'll do these two together. Okay, now with this, let's take a look at an example, right? Let's take a look at an example. So now you should know how to do the calculations. So example, okay, determine the design moment at the critical sections using the ACI moment coefficient. Ooh, sorry. ACI moment coefficient. Okay, for the following slabs. Okay, for the following slabs. Keyword slab. Okay. Now concrete F prime C equal to a 4 KSI. Fy yield strength equal to a 60 KSI. Okay, just give me a minute. I'm gonna get a water. All right, sorry, I'm back. Okay, so let me draw the slab, right? The slab has a nice geometry like this. And have 3 spans. Okay, 3 spans. All right, and the beam underneath is 12-inch. And the height of the slab is 6-inch. Okay, and the height of the end spandrel is 22-inch. Okay, and with a D, depth 19.5-inch. These are given. These are all given. Okay, now 3 spans. 3 spans. End span has a span length, middle of the beam, 13 feet. Sorry, 13 feet. Okay, the middle span have a 15 feet. And a live load is 150 PSF per square feet. And the dead load tells you just the self weight. Just the self weight. Okay, so first of all, coefficient, right? So confirm ACI moment coefficient. Can be used. So to check whether it satisfies all the limitations. So first of all, how many spans? So 3 spans. Okay, 3 spans, so check. Makes sense. Okay, and span length, like longer span length, right? So 15 feet, shorter length, 13 feet, equal to 1.15. So within the 20% requirement, right? So also check. Okay, also check. Now the dead load equal to a HF, right? This is the height of the span, HF, 6 inches multiplied by 150 PCF. Okay, I have a per foot, don't forget per foot unit built in, and this is 75 pounds per square feet. So live load, okay, stop working again. So live load, sorry, my Apple Pencil, probably because it's forgot to charge it over the weekend. All right, let's see if it works. So the live load divided by that load equal to 150 divided by 75. And that is 2, which is smaller than 3. So check. Okay, and of course, this is prismatic. Okay, so prismatic check. So that means I can apply moment coefficient. All right. So in the exam, of course you can, but I want to see this if this is the problem. Okay, if this is a problem. And second, let's do calculations, right? So to determine the moment coefficient. Okay, so I'm gonna refer back to here, back to here. Okay, but let's be careful a little bit. Let's be careful a little bit, right? This is span less than 10 feet. We cannot use it, right? We cannot use it. We have to use a different one. Okay, so I'm gonna take the beams. Okay, I'm gonna take the beams and I'm gonna take this one right here. Okay, I'm gonna take this one right here. All right. Okay, and then I'm gonna take all this right here. So let me just try to get this out. Okay. You have it with the notes together, Sean. If you haven't noticed from previous notes, right? Where I'm always posting this, okay? So this is the list of the coefficient I'm gonna choose, okay? So I'm gonna write down here. I'm gonna write down here specifically, right? So simplify a little bit. I basically have a slab and I have a simply supported, not simply support, I have a support condition here, support condition here, support condition here, and support condition here. Okay, so let me give some names and I call this A, where's that here? B in the middle, let's call it here. C, which is in the middle here, in the second support here, and D, which is the middle here. Okay, now at A, I'm looking for a negative moment. Okay, so let me use red to differentiate. So mu negative equal to minus 1 over 24 omega u Ln squared. Okay, B, I'm looking for a positive moment, so it's positive 1 over 14 omega u Ln squared. C, again, I'm looking for a negative, so it's a negative 1 over 10 omega u Ln squared. And D, I'm looking for positive, so 1 over 16 positive omega u Ln squared. And actually, these the rest of it, this is minus 1 over 10 omega u Ln squared. This is symmetric. And now for this positive, I actually have 1 over 14 omega u Ln squared. And the far end is 1 of minus 24 omega u Ln squared. Okay, from the table. And notice that the symmetry is right here. Center line symmetry is right here. Okay, so first thing first, I need to determine my omega u. So omega u equal to 1.2 dead, which is 75 pounds per square feet, plus 1.6 live, 150 pounds per square feet. So I got a total of 330 pounds per square feet and equal to a 0.33 kips per square feet. Okay, and now I just want to make sure, right, to see omega u dead load only, and that is equal to 1.4 dead load, 75 PSF. So that is 105 PSF. Okay, so among these two, this fellow here governs. What do we mean by governs? Means it's bigger than 105 PSF. Remember, so omega u is bigger than 1.4 omega dead load only. So this is also the other criterion has to be satisfied to use the moment coefficient. Okay, so with that, it means, okay, I can use these numbers here. I can use these numbers here. Okay, so I'm gonna write them down. Now, a moment mu equal to a minus 1 over 24 omega u 0.33 kips per linear foot. And don't forget this is per linear foot, per foot, because we're talking about the strips here, okay? And then this is Ln, which is 13 feet, clear span, okay? So 13 feet, so LN here, 13 feet minus 12 inches, right? So minus half of 12 from the left, minus another half from the right, okay? This is also 12 inches, okay? Don't forget. So that is 13 minus half, okay? So I end up with a minus 1.98 kips feet per foot. And remind you, in the exam, I'll be looking for this unit here. Has to be kip foot per foot. Now, where that per foot come from? Refer to the previous lecture, okay? Refer to the previous lecture. So B, mu equal to a positive 1/14, 0.33, same unit here, and 13 minus 1, same thing here, and equal to a positive 3.39 kips feet per feet. Okay, C, mu equal to minus 1/10, 0.33, same unit. Here, now this is C. C is right here. This is the negative moment, okay, as support with two adjacent spans. Two adjacent spans. So Ln equal to half of Ln1 plus Ln2. Okay, so Ln1, Ln2. All right, so now this equal to half of, on the left, 13 minus 1, on the right, 15 minus 1. Okay, that's the clear span. So I got a number of minus 5.58 kip feet per foot. Last but not least, D, mu equal to positive 1/16, 0.33. Okay, 15 minus 1, so that is a positive 4.04 kip feet per foot. Okay, sorry, don't like this to be long here. Okay. All right, guys, that's it for the continuous beam moment. Okay, I'll upload both the notes and video to YouTube and Canvas. Okay, so you take a look at them. But quick review. All right, before you apply the moment coefficient, you have to satisfy all these requirements. Okay, and then also omega u here, right? You have to make sure which one is your omega u. Which one is your omega u? Okay, be careful about it. Are they in squared? Are they, no, where is it? Oh, so sorry, here, I forgot, you're right, thank you. Here, 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 here. Okay, thank you very much, Helen. Sorry for the mistake. Okay, all right. Okay, so now once you confirm you can use it, then the rest of it is pretty straightforward. Okay, all right, now we have finished the beam and one-way slab. So you should be able to do your homeworks, okay? Again, I will let you know once I finalize the exam, and we have a chat again tomorrow, Tuesday, for office hour, 2 o'clock. Don't forget, okay? Same link as I sent before, all right? Now, we're going to enter the serviceability for the next lecture on Wednesday, okay? So keep in mind that we might have a little bit of gap between now and the exam, so you have time to study. But the warning, okay, the exam are not easy, okay? The exam is not going to be easy, okay? All right, thank you very much. That's it, guys. And I see you on tomorrow, actually, 2 o'clock for office hours, okay? All right, bye now.